and fly away with me. Come and fly away with me. Come and fly.
What's good, guys? Welcome back to another video. Yeah, but today I have the 2007 chemistry paper, and I'll be going through that today. By the way, I hope you're loving the new intro. Of course, I'm going to make a few adjustments to it, but not now, exam time and stuff. But anyways, you know what to do. Drop a like, drop comments, and most of all, subscribe and do the dirt. Go down to the description and please click on both Instagram links and follow. Anyways, let's get started. Alright, so question 1. Which of the following diagrams show the correct behavior of protons, electrons, and neutrons in an electric field? So we know that the electrons will go towards the positive plate, and the protons, because they're positively charged, will go towards the negative plate. However, because the electrons are lighter or relatively lighter than protons, they will bend or deflect at a greater angle. So looking at these, we would have to choose A. Yuppie. A. This deflection thing though is only true if the particles have the same energy. So let's continue. This says, what is the average relative atomic mass of bromine given the following isotopic masses and relative abundance? Now we have a 50.5%, that's 50.5 over 100, times, what's that, 79, and we're going to add this value here to 49.5 over 100 multiplied by 81, and let's put that into the calculator. So 50.5 over 100 multiplied by 79 plus 49.5 over 100 times 81, that gives you 7,999 over 100. That's literally 79.99 in decimal. Yup. Alright, number 3. I'm going too far down. Which of the following is not true for period 3 of the periodic table? Argon has the highest first ionization energy. Phosphorus has a higher first ionization energy than sulfur. Aluminum has a higher first ionization energy than magnesium, or first ionization energies decrease from phosphorus to aluminum. Right, the answer 3 is C. Aluminum does not have a higher first ionization energy than magnesium. It's rather the opposite, because of the fact that when you go to aluminum, you enter the d orbitals, the 3d orbitals, right? And it is we think that, or we assume that, because we're still in the third sublevel or the third shell, the d orbital is a bit further away from the nucleus, therefore the electrons there would be pulled on less by the positively charged nucleus. Therefore, it would be easier to remove the electron from aluminum, the electrons from aluminum, than the first electron from magnesium. So 3C. Number 4. Which of the following pairs of elements would be expected to form the compound with the most ionic character? So that would be the most electronegative element on the periodic table as fluorine, and the least electronegative element there, right? So that would be B for number 4, rubidium and fluorine, because fluorine is the furthest up and the furthest to the left, and of lithium and rubidium is the furthest below and the furthest to the right. Great. All right, number 5. Item 5 refers to the displayed formula for the amino acid glycine. Okay, that's because of the R group here, it's just a single H, that's why it's glycine, given below. What are the approximate values of the bond angles, angle A and angle B, in the compound? All right. Okay, so looking at the angles A and B. All right, we have 1, 2, 3 bonds here, so it's safe to assume that it's trigonal, right? However, this nitrogen here will have a lone pair of electrons. So two electrons, which make a lone pair, right? This lone pair will force the bonded pairs closer together, the bonded electrons closer together. Therefore, it will have a molecular geometry or angle lower or less than 120 degrees. So it's either A, B, or D. And here, 1, 2, 3, these double bonds here, this double bond here can be counted as a single pair, right? So we will have 1, 2, 3. Yeah, I'm correct. 1, 2, 3, right? That's trigonal. So it's 120 degrees. So the answer for number 5 is A. It would also have to be less than 109.5. So that's why we wouldn't go for D. Number 7. Analysis of an unknown compound X shows that it contains 0.4 grams of carbon. So we have carbon. We have 0.06 grams of hydrogen, and we have 0.5 grams of oxygen, right? So we have 0.4 here, 0.06, and 0.5 grams. Now we need to find out how many moles this is, right? So 12 grams is equal to 1 mole here. 1 gram here would be equal to 1 mole. And 16 grams here would be equal to 1 mole of oxygen. So we want to find 0.4 is equal to X. Let's say that. 0.06 is equal to Y. And 0.5 is equal to Z or Z. 12 cross multiply, 12x is equal to 0.4. Therefore, the amount of moles would be equal to 0.4 over 12 or divided by 12. and that is 0.03 moles. And the same thing here, 1y is equal to 0.06, and this will lead us to having y being equal to 0.06 moles. And here we have 16z being, or 16z being equal to 0.5. So 0.5 over 16 is equal to 0.03. And that would be in moles as well. Now divide everything by the smallest number of moles, and in this case it's 0.03. So 0.03, 0.03, 0.03. 0.03 into 0.03 is 1. 0.03 into 0.06 is 2. And again, 0.03 over 0.03 is 1. So we have a CH2O, because 1 carbon, 2 hydrogens, and 1 O. So the answer for number 7 is B, as in boy. Yes. Number 8 says, in the following redox reactions, including chromium compounds, what is the oxidation number of chromium in each compound? All right, we have the Cr2O72-. So first of all, we have 2Cr plus oxygen has -2, so -2, and we have 7 of those, so multiplied by 7 is equal to the entire thing has a charge of -2. So 2 sevens is 14, so that's -14. So 2Cr minus 14 is equal to -2. Bring over or add 14 to both sides, and you'll have 2Cr is equal to -2 plus 14. Because if you have Cr, I skipped a step, it would be Cr minus 14 plus 14, and those 14s would cancel out, is equal to -2 plus 14. Now -2 plus 14, seeing that 14 is larger, you subtract the numbers, so you'd have 12, and because 14 is larger, you'd have plus 12 is equal to 2Cr. You want to find Cr, so divide 2 by both sides. You'd have Cr being equal to plus 6. So here we have the answers either A, B, or C so far. Now let's look at Na2Cr04. Alright, Na has a charge of plus 1, so, and that's 2 of them, so it's 2 plus the Cr, and as I said, plus the -2 for the O times, how many is that? We have 4 O's, and the entire charge is 0. It's neutral. Alright, so 2 4s, 8 I believe, and we have -8. This will be plus 2, and the Cr is equal to 0. 2 from 8 is 6. We have -6 going on for us here, is equal to 0. Cr is equal to plus 6 if we bring 6 over, or add 6 to both sides, same thing. So we have this being plus 6, so it's either A or C. Now let's look at Cr2O3. Now we have 2 Crs, right? And we add the -2 and the 3 oxygens. That's 3 twos is what, 6, and the overall charge again is 0. You see there's no charge here, so it's 0, right? So 2 3s is 6 minus 6. 2 Cr is equal to 0, and 2 Cr is equal to plus 6 if you add it to both sides, and we divide by 2 on both sides because we just need Cr. 22 1, 26 3. So Cr here is equal to plus 3. So the answer is C. So number 8 is C. Hope you're getting this. Yup. Alright, let's continue. So number 9. which of the following does not represent a balanced redox equation? From this, I'm assuming that all are redox, but let's check. All right, let's just look at zinc here, has an overall charge of 0. Here it would be +2. This is obviously redox. I've seen this so many times, I don't have to check that. This as well. Let's look. Br2 here is 0. Br here has a charge of -1. So it was what? Reduced here. This was oxidized, the zinc. Here tin is 0, and here it's +2. So this is also a redox reaction. So we're looking for the one that's not balanced. And here we have 1 tin, H, 1H, but 2H over here. So we'd have to put a 2 here. N, 1N, I guess. And 3 O's, but this is 2, 4, 5 O's. Okay, so the 2 here wouldn't really help, but this isn't balanced, and it's... So 9 is D. Should I check the others? I don't think so. I don't think I need to though. Let's give it the benefit of the doubt. Number 10. When solutions of iron 3 nitrate and potassium iodide are mixed and starch added, a blue-black color is formed. Which of the following reactions are involved? No. This one, of course. So is it Fe? I don't know. It's not. It was not reduced to Fe solid. So this one. So 1 and 3, is that there? 10 is A. Yes. Great. Let's move on to number 11. Fancy. Okay, so this says if 88 grams of solid CO2 evaporates, how many liters of CO2 gas or carbon dioxide gas will be formed at a temperature of 27 degrees Celsius and 2 atmospheres of pressure? The universal gas constant R is equal to 0.0821 atmospheres. That means we're getting the volume. That's what it asked, yes, in dm cube, but they didn't put any what do you call these now? They didn't put the units for the answers. All right, so we're told 88 grams of carbon dioxide. So we have to find the number of moles because we'll be using the equation PV is equal to nRT, where T is in Kelvin. So we're also gonna have to change this 27 degrees Celsius to Kelvin temperature or absolute temperature. So 27 plus 273.15. You don't have to put the 0.15, but I like to put it because it makes it more fun. Alright, so that would be putting that in Kelvin, so we can just leave that right there for now. Now we need to find the number of moles, and we're told that it's 88 grams of carbon dioxide. So 1 mole of carbon dioxide is equal to 12 plus 32, because 16 times 2 is 32, right? Yes, so that's that. And think that's 44 grams, right? And we need to find the number of moles, and is equal to 88 grams. And off the bat, that's 2, because you know you're gonna have 44. Let me just write the whole thing out. 44n is equal to 88, and we need to find n, so we divide by 44, and that's 2. Yes. So the number of moles is equal to 2 moles. I need space, so I'm going to take this out here. I'm so sorry. So we found out that it's 2 moles. So let's just record that here. 2 moles. Right? And we're trying to find the volume. So we'll eventually divide by the pressure. And we are already using atmosphere, so there's no conversion needed there to pascals or anything. We're going to use R here in atmospheres as well. And we're going to get to our answer in dm cube. So 2 moles times 0.08 0.21 atmospheres times the 27 plus 273.15 all over the pressure, which is also 2 atmospheres. And let's put that in the calculator and see what we get. 0.0821 times 27 plus 273.15 times 2 all over 2. 2's are going to cancel each other, I think, but let's not rely on my brain and math. Let's use the calculator, and I got 24.6, and 11 is A. Okay, number 12. Which of the following statements about the liquid state are true? So, volume of the liquid is constant at a particular temperature. I believe that's true. The density usually decreases with increasing temperature because, yes, it changes state. It goes from liquid to gas, and the gas is less dense because of the spaces between the particles. And it is difficult to compress, I believe so. So all three. 12 is D. Alright, let's move back to 13. Okay, you need to know the definition for these. Enthalpy of formation, lattice energy, enthalpy of solution, enthalpy of hydration, enthalpy of atomization. All of those, you need to know them. So, items 13 to 14, and bond energy. They're probably more, but I can't remember right now. Refers to the following options. A, enthalpy of formation. B, lattice energy. C, enthalpy of solution. D, enthalpy of hydration. Now it says, match each item below with one of the options above, each of which may be used once, more than once, or not at all. Alright, so we have X here, and it's an ion, and it's in its gaseous state. And also here we have another ion in its gaseous state, and we see where it forms a compound that's in its solid state. And this is 13. This is lattice energy of formation. Now we hear X here is in its solid state, and Y2, or the molecule of Y here, is in its gaseous state, and it forms a compound that is solid, and it's 1 mole of that as well. And you see where these now are in their standard state. So this is the enthalpy of formation. So 13 is B and 14 is A. So review those definitions and you should be fine. Alright, so number 15 says what is the standard heat of reaction? So we're finding heat of reaction, delta H of reaction, at 101.325 kilopascals of pressure. That's standard pressure, and that's 1 atmosphere, and 298 Kelvin, which is 25 degrees Celsius. That's room temperature. So, and that's standard temperature as well. Alright, we see Zn solid and Cu2 plus, Zn2 plus, and Cu solid. Alright, now to find the heat of a reaction, PR, you subtract products minus reactants. Your judgment though. I can't deal with this. Okay, P is for products, R is for reactants. PR, like PRO, that's how I remember it, PRO. So PR, so R, you subtract the heat of reactions from the P, the heat of the products, and seeing that these are our reactants and these are our products, we're going to put the products first, and this would be 0 as you see here. Zn2 plus, on the other hand, is negative 152.4, and we're supposed to subtract reactants R and 0 and 64.4. Subtract 64.4, and I got 216.8, and that's negative 216.8, and that's, if you round it to the nearest whole number, it's negative 217. Great. All right. Item 16 refers to the following reaction which occurs in the presence of dilute acid. So that's the equation right there telling us what reacts. And it says if the rate equation for the reaction is rate is equal to K, that's the rate constant, and the concentration of CH3COCH3, is that acetone? I don't know, but it says it's an acid, so that can't be acetone. Is acetone an acid? I don't know. I don't think so. Anyways, let's continue. Concentration of the H plus ions, and yes, multiplied by that. Which of the following best illustrates the slow step? The slow step represent. We're going to look for whatever is in the rate equation. Seeing that iodine is in the equation but not in the rate equation, we can't choose one with iodine, and we see where B has iodine, C has iodine, and D has iodine. So the answer here is A. We look for what's in the rate equation. There you go. Number 17 says, which of the graphs below best shows the change in distribution of molecular energies when a gas at T1 is heated to temperature T2? We have to find one where the peak, or the top here, moves a bit further over, and we see where, let's say if this is the activation energy, you have more particles having energy greater than the activation energy. So the answer here is B, as in boy. That's 17, right? I believe so. Let's move on to number 18. All right, it says oxidation of ammonia is one step in the commercial manufacture of nitric acid. All right, that's the equation right there. We're told that delta H is minus 908 kilojoules per mole. That's telling us that the forward reaction is exothermic. It says which of the following would not have an effect on the position of the equilibrium? Addition of ammonia. If you added ammonia, that's NH3, the equilibrium would shift to the, I write with my left hand, so this is right. It shifts to the right in order to produce more products, or to restore, in an effort to restore balance in the reaction here, seeing that we're dealing with dynamic equilibrium and Le Chatelier's principle. B says a decrease in the temperature. If you decrease the temperature, the equilibrium will shift to the right as well, because it favors what? It's an exothermic forward reaction, so more products will be produced. And if you increase the pressure, that will also shift the position of the equilibrium. However, if you add a catalyst, all that would do is speed up the reaction, but everything will remain the same or constant in order to, or the equilibrium will still be there. So that would not have an effect on the position of the equilibrium. C. All right, let's move up to 19. Says which of the following statements does not refer to a system in equilibrium? A, the rate of the forward reaction is equal to the rate of the backward reaction. That is true. The amount of all the species in the system remains constant. That sounds a bit fishy. Let's continue though. The concentration of all reactants and products are equal. C. No, that's not true. The reaction is reversible. Yes, it is. That's why you have forward and backward reactions. It's reversible. So C for 19, because if it were true, that means that the Kc, or what's that, the Kcs would be 1. And that's not true for all equilibrium reactions. I hope I said that correctly, or you understand what I'm saying. I think it's correct, yes. C is for 19. Number 20. Which of the following are Bronsted-Lowry bases? Bronsted-Lowry bases are proton acceptors. You know, they accept the H plus ions. In this case, OH minus would accept 1 and would get water, and the H2O, water itself, that's the guy, yes, would get 1 and would get the hydronium ion, or is it a hydroxonium? The H3O minus ion. So 1 and 3. 20, we have A as our winner. Alright, let's go down to 21. It says, item 21 refers to the following information. Scientists have invented a new indicator called Sure pH check, creative, shown in the diagram below. Alright. Says, what is the H plus ion concentration of the acid in the container X shown below? Alright. So this looks like this right here, that 2.5 thing. They're testing my artistic abilities now. Anyways, so we know that for an acid or strong acid, the pH is equal to minus log to the base 10 of the concentration of the H plus ions, and they're asking for the H plus ion concentration. We know that the pH is 2.5, so the minus or the negative pH would be equal to log to the base 10 of the concentration of the H plus ions. So in order to find the concentration of the H plus ions, we'd have to find the antilog, and that's 10 to the minus pH, the antilog of the negative pH. So that would give us the concentration of the H plus ions. On your calculator, you should see where you see log above that. I think you click shift. I don't know if you do this on all calculators, but on mine I hold shift and then the log key, and that gives me the antilog, and the negative pH would be minus 2.5. And there I got on my calculator on 3.1622776 times 10 to the minus 3, but we're rounding that up, so we're going to have 3.2 times 10 to the minus 3. So 21 is A. Alright, let's go down to 22. It says, which of the following indicators are suitable for a titration of aqueous sodium hydroxide with aqueous ethanoic acid? Alright, sodium hydroxide is a strong base, let's say SB for strong base, and ethanoic acid is a weak acid, so let's put WA for weak acid. Right, so how I do this, I usually just write the scale here to make it easier. So 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. And I have a strong base, so I'm gonna start like right here. And I have a weak acid, so I'm gonna go up to about 6 or 7. Connect to these. And then I find like the midpoint on my line, and it's like right there, and I see 10. So it would fall about, you can't use a range of 2.9 to 4.0, it falls out of range, right? 9.1 to 9.6, probably, seeing that you're asking for 2, would probably fall in the range there, so I'd go with that. 4.2 and 6.3 falls out, so no. And here we got the perfect looking one for what I did here, and it's 10.1 to 12.0, so 2 and 4, so 22 is D. And I think we got that right there, looking nice and smexy. 23, the titration curve of a weak acid strong alkali or strong base is, alright, weak acid, was that what I did here? Strong base, so it's like something resembling that. Now this here is too far down. It looks like a strong acid thing going on for it, so no. Here as well, so that's no as well. This one here seems okay, I guess. It's not the furthest down, and this would be weak base, weak acid, because here there's no definite, or it's hard to pick up where the equivalence point would be, and that often happens when you do weak base, weak acids. That's why there are no really suitable indicators to test this thing. I think they use electrical methods, let's just say that. So 23C. Alright, 24, let's look at that. Which of the mixtures below will form a buffer? To form a buffer, you use a weak acid and the salt of that weak acid. So aqueous ammonia could be used as a weak acid because ammonia is amphoteric, meaning it shows both basic and acidic properties. But calcium hydroxide is not a salt of ammonia, so no. Aqueous ammonia and aqueous ammonium chloride, I would say yup. Ethanoic acid and aqueous calcium ethanoate, very much so. And here we have aqueous ethanoic acid and aqueous benzoic acid. These are two acids, not even an acid and a salt, so no. So 2 and 3 would be the answer for this, so B. I'm going through this quickly though, it's like 30 something minutes. Alright, 25. Alright, equal volumes of 0.1 mole per dm cube aqueous ethanoic acid with Ka being equal, or acid dissociation constant being equal to 1.8 times 10 to the minus 5 mole per dm cube, and 0.1 mole per dm cube aqueous sodium ethanoate are mixed. So we have a buffer here, and the pH of the resulting solution is, the pH of a buffer is, there are two ways to do it, but I'm gonna do it the easy way or the easier way for me. Alright, have minus log. Alright, let's not say that. Let's say pKa plus minus log to the base 10 of acid over salt, I believe. So here, pKa is equal to the minus log to the base 10 of Ka. So let's say pH is equal to minus log to the base 10 of Ka plus log to the base 10 of this 0.1 over 0.1, which is 1, and the log to the base 10 of 1 is 0, so the pH would be equal to minus log to the base 10 of Ka, and let's put that in, or the pH is equal to pKa, so minus log to the base 10 of, what's that, 1.8 times 10 to the minus 5 is equal to 4.74. Alright, I must say I'm off by a bit, but 25C. Alright, let's go down to 26. The solubility product of iron 3 hydroxide is affected by a change in both temperature and the concentration of the Fe3 plus ions. If it were a gas, then pressure would affect it. So 1 and 3, 26C. (27) Which of the following would form part of a standard hydrogen electrode? So in order to do that, you'd have to have a temperature of 298 degrees Kelvin, or that is 25 degrees Celsius, and we don't have that here. 1 atmosphere is indeed okay. 1 mole per dm cube of a, let's say, monoprotic or monobasic acid. Sulfuric acid is a dibasic acid. Therefore, in 1 mole, with a concentration of 1 mole per dm cube, you would have like 2 moles of H plus ions per dm cube instead of 1 mole per dm cube of H plus ions. So 2 is not correct. 3, a length of platinum wire. Yeah, I guess. So 27 is B, sorry. 3 only, not C. 3 only, which is B. Oh my god. 28. Alright, so this says the electrode potentials of 2 half cells are given below. So we have the chromium 3 ion there, and what is that? It is reduced, and we have the zinc right there as well, and it's also reduced. Now it says, what is the cell potential when these 2 half cells are connected? The easiest way to find this is subtract the more negative electrode potential, and the more negative one there is 0.76, so minus 0.41 minus, in bracket now, minus 0.76, that is 0.35, and that's plus 0.35, so the answer is C. But let me write that down so you see what I'm saying. Minus 0.41 minus 0.76 volts. That whole thing is volts. And you should get this, C. Oh, 29 is like right there. 29 refers to the Daniel cell illustrated below. Which of the following statements is not true about what happens in the cell after it has been running for some time? The blue color of the copper sulfate fades. Ions in solution cross the porous medium. Yes, that's the zinc electrode reduces in size because it's oxidized, and D, the copper electrode remains unchanged. 29 is D, that's not true. the copper electrode will not remain unchanged. Probably gets fatter. Alright, let's see. We have 30 here saying the units of the rate constant K for a second order process is, alright, so we have the rate being in mole per dm cube will be equal, per second, don't forget that, it's a habit for me to forget it, don't forget it though. Per second is equal to the constant, that's the rate constant K, and say it's in second, or it's a second order process. Let me be lazy and just put A to the set 2. I could also put A times concentration of B, and that would also be a second order. So this now would be, the concentration there would be mole squared dm to the minus 6, right? And I'm supposed to divide this by this, so mole per dm cube per second all over mole squared dm to the 6 minus 6 is, alright, mole, cancel that, we'll have 1 mole there, and this going to cancel that, we have 3 there, and we'll have, seeing that this is minus 3 and below, it would be now dm cube mole to the 1, under here would be per mole, and we have per second up there, we keep that per second. That would be the answer, dm cube per mole per second, dm cube per mole per second. 30 is A. Great. There's also another way you could write that out and it not let it not be so confusing. Would have mole per dm cube per second. Seeing that we're dividing by this, would multiply by per mole squared and dm to the 6 instead of per dm, and this would cancel this and would have 3 dm cube. This would cancel this and would have per mole, and would have the per second still here, per mole, and the dm cube, and still got 30 as A. Alright, says which of the following elements has the highest electrical resistance? The one that, the least conducting one. So probably a non-conductor. Metal, these are metals, so they conduct, and this is a metalloid, so it's a semiconductor. So B would have the highest resistance. Let's continue to 32. Okay, items 32 to 33 refers to the following oxidation states. You have the +1, +3, +4, and the +5. And it says match each underlined element with its oxidation number. Each oxidation number may be used more than once, or not at all. 32, we're seeing silicon here. It's +4, but let me show you why it's +4. So we have silicon plus, the Cl has a -1 charge and it's 4 of them, so we multiply by 4 and the overall charge is 0. We'll have -4 here, Si -4 is equal to 0, therefore Si is equal to +4 if we add 4 to both sides. This would cancel each other. Si is equal to +4. Therefore, the answer for 32 would be B, as in boy. That's a lie. Swear I have dyslexia. C with the +4. Now, aluminum, it's in group 3, so it generally has a oxidation state of +3, but let's work it out and show you that it's really that. Let me erase these. get more space. Oh my god. Alright, so we have 2 aluminum atoms, and we have the chlorine, which I told you was -1, and we have 6 of those, so multiplied by 6, and the overall charge of that entire compound is 0, and 6 times 1 is 6, but we have a negative right there, and we have 2 aluminiums, and it's equal to 0. 2 aluminium is equal to +6 if you bring it over. Don't need to put the plus, but I just put it there to keep you informed. Divide by 2 on both sides. 22 is 1, 26 is 3. We see that aluminum has a oxidation number of +3, and that's for aluminum. ON is oxidation number. Let me just not confuse you. So that's B for 33. Alright, let's move down to 34. Says, which of the following trends is observed on going left to right across period 3 of the periodic table? Now it says acid strength of the oxides. Should I make bloopers for these things? I swear. Acid strength of the oxide of the elements increase. Yup, I know that's true. Because, alright, you start with ionic characteristics. When you get to like aluminum and the metalloids, you have them displaying, or aluminum compounds displaying both, what will we call those again? Basic and acidic properties. That's why you get amphoteric, and then as you progress it gets more acidic. So I know A is true, but let's look at the other answers. So electropositivity increases. No, generally as you go across a period, the electronegativity increases. Electropositivity decreases. As you go further towards the left, on the other hand, the electropositivity does increase and the electronegativity decreases. Now the ionic radius decreases. Though this is true in a sense, let's see where the hiccup gets. All right, as you go across the group, the period, you have first the metals, and those will lose an electron in order to form a cation. Yes, they get smaller, but when you get over to around where period 5, let's say period 6, they start accepting electrons and forming anions. And anions, seeing that for cations you lose the outer shell, or yes, you would lose the valence shell, and cations, they keep their shell. Anions are bigger than cations, so the size there, the ionic radius, does not decrease right there. But if you're comparing just cations, the ionic radii do decrease. And if you're just considering the anions, then the ionic radii decreases. But generally, for going from left to right, it's not true. The metallic character increases. That's a lie. It doesn't. If anything, it decreases. 35. On descending group 2 of the periodic table, which of the following statements are true about the elements? We're going down. So they lose electrons more easily. That means that there is more ease of ionization. So the ionization energy decreases, meaning it requires less energy to remove an electron. So that is true. Their atomic radius increases. Yep. Because each as you go down the group, you enter another period, and as you enter another period, there is another energy level. And number 3, their ionization energy decreases. I said that, it's true. The electronegativity decreases. Yes. So all 4. Remember, electronegativity on the periodic table generally increases up from bottom to top and from left to right. So 35 is D, and let's go to 36, see what that has to say. Says silicon tetrachloride reacts with water, but carbon tetrachloride, I also think that is tetrachloromethane, but yes, does not wait, what? Silicon tetrachloride reacts with water, but carbon tetrachloride does not, because carbon A has a higher ionization energy than silicon, B has a more stable +4 oxidation state, C is a nonmetal, and silicon is a metalloid, where carbon has no available orbitals of energy required for coordination with water. And there we go, we got D as our winner. 36 is D. 37, carbon monoxide is easily oxidized to carbon dioxide, whilst lead 4 oxide is easily reduced to lead 2 oxide. What deductions can be made from this information? The 2+ oxidation state of carbon is less stable than the 4+ oxidation state. Yes. The 2+ oxidation state of lead is less stable than the 4+. If this is true, this can't be true. On descending group 4, the +4 oxidation state becomes more stable relative to the +2, and that's not true. It's the opposite rather. On descending group 4, the +2 oxidation state becomes more stable than the relative to the +4. So this is, I believe, is what that says. Yes, what I just said is what this says. So 1 and 4. Answer for this is C. I pray. 37 is C. 38. On descending group 7 of the periodic table, which of the following trends is true? Volatility increases. No, as we go down group 7, the volatility doesn't increase, because let's see, fluorine gas, chlorine gas, bromine liquid at room temperature. Which one is next? Iodine. Iodine is solid at room temperature, and it's assumed that astatine, based on the trend, is solid as well. The color becomes lighter and less intense. No, the color becomes darker and more intense. Because, alright, let's say again. Fluorine is what? Pale green. Chlorine yellow, or something like that, or pale yellow. Bromine is red, brown, brick red, deep red, dirty red. What's next? Iodine, purple. When it sublimes, it appears gray or silvery or black when in its solid state, if you just look at it like that, but it sublimes purple. And yeah, that's where it ends. We don't know the color of astatine. The relative stability of the hydrides increase. That's not true, because as you go down group 7, the atomic radius gets bigger and bigger. That means that when they bond, or the hydrides, when they bond, the bond length gets longer because they're further apart, so the bonds become weaker, and that's where we get D from. Yeah, D. That's it, believe that the hydrides of the elements become weaker. Yes, bond length increases, bonds become weaker. Shorter bond length, stronger bonds. Yes, so 38 is D. 39. The precipitate observed when iodine ions react with silver nitrate or aqueous silver nitrate is insoluble, yes, in dilute nitric acid and aqueous in ammonia. Number 40. A characteristic property of transition metals is the presence of a partially filled D sublevel. Yes, that's the definition. 41, argon, that's the core. 3d5 is the electronic configuration shared by both. Alright, this is telling me that, oh my god, don't mark that there. 18 plus 5, so I need to find 18 plus 4, 23. Manganese is 25 minus 2 because you have a plus 2 charge. That is indeed 23, but cobalt, 27 minus 3 is 24, so that's not it. Manganese, as we said, the 23 quarter. Iron, 26 minus 3 because that's 3 plus. That does have 23. Iron, yes. Chromium is 24 minus 3 is less than 23. Chromium minus 2. 24 minus 2 is 22, not 23, so that doesn't meet it either. So the answer for 41 is B, as in boy. It's also important that you remember the exceptions for both iron and chromium because of iron's full or almost full. I believe that it has like, alright, 9 electrons in the d orbital, but no, it does not. It has 10. It sways from the norm really because of that. Let me write that down for you to better understand what I'm trying to say. 1, 2, 3, 4, 5. So the 4s for iron has this only 1 electron, and the rest have 2. They're paired. Now the reason for it only having 1 electron in the 4s is due to the fact that if this electron here, this one here, were to go in that 2s, this would have a almost filled d orbital, and it's better stable with it filled, so the one electron from the 4s just jumps over into the 3d right there to fill the space and have it become in its most comfortable position per se. And it's the same for chromium, except for the fact that chromium is like half that instead of having, it has 1, 2, 3, 4, 5 instead of 10 in the 3D. Let me move on because I spent a lot of time trying to explain that. But we still ain't 1 hour and 30 minutes. That's all we have to do the exam. So talk to me nice. Items 42 to 43 refers to the following options: A central ion in a complex, B a ligand, C an octahedral complex, or D a tetrahedral complex. Match each underlined item below with one of the options above, each of which may be used more than once, or not at all. 42. Now cobalt is what underlined, and that is the central ion in the complex. So A for 42. 43 underlines the entire complex. Now, how do we decide whether it's octahedral or tetrahedral? We look at the coordinate number. The coordinate number is 6, which tells us that it's a octahedral complex. If it were 4, then it would be a tetrahedral complex. So 43 is C. 44. Oh my god. Item 44 refers to the following information. Now, aqueous sodium hydroxide, and it's placed in aqueous, what do you call that now? Ammonia, X2 plus ion, whatever that ion is, we don't know. That's what we're testing for, we're trying to find out. Now it says white precipitate soluble in excess, white precipitate insoluble in excess. It says which of the following reagents does not aid in the identification of the X2 plus ion? Nitric acid, because you will form, when it's with nitric acid, you will form the X2 plus nitrate compound, and all nitrates are soluble, so you still wouldn't know what it is. 44 is A, the last one. Thank you. 45, an unknown salt solution containing a single anion is tested with lead 2 nitrate solution followed by dilute nitric acid and HNO3. A white precipitate is observed which dissolves in acid with effervescence. These observations indicate the presence of two anions that, give off bubbles, or give off gas to produce bubbles in the solution. So it may be the carbonate, but it can't be chloride. Sulfide, yep, not sulfate though. Sulfate doesn't do that. So here we have the yep, and yep, but we don't have the sulfate, nope, and we already said no to those. So 45 is C. And we're done. Yeah, we're done. Yes, so again, as I always say, if you're hearing this, that means you've made it to the end of the video. Congratulations, you know what to do. Like, subscribe, go follow me on Instagram, both on my business page and my main page. Yeah, so until I do another one, do the dirt, subscribe, do the nice stuff. Yeah, I think I'm done. Yeah, the hardest thing to do is the outro. I'm like, what am I saying? Anyways, I'm done, so bye guys.